In past videos, we've talked a little bit about dynamic equilibrium, which is just when the rates of two opposing processes are equal. So just kind of a generalized definition of equilibrium. But I want to talk today about equilibrium constants and chemical equilibrium. So looking at chemical reactions and kind of using these what are called equilibrium constant expressions and the magnitude of those numbers to give us some information about the chemistry and the reactions themselves. So for chemical equilibrium, what we're talking about is the rate of the forward reaction being equal to the rate of the reverse reaction. So the forward reaction is as it is written in the way that we normally look at and think about a chemical process. So reactants to products is the forward reaction. The speed of that is equal to the speed of the reverse reaction, which is where the products are going to the reactants. So we write that reversible process with these arrows that are kind of going in opposite directions, which say that both of these things are happening simultaneously. And when they happen at the same rate, then we say that they're in equilibrium. Now the equilibrium constant is K. KEQ is usually the subscript that you use. You'll also see KC. C is for concentration. EQ, of course, for equilibrium. There are many subscripts that will be on this K, kind of depending on the different application of it. You'll see Ka, for example, for weak acid equilibria, Kb for weak base, Ksp for solubility products. That kind of goes above and beyond the level of this particular video. So the subscript you'll see in various kind of contexts, they all mean the same thing. They have the same expression. So these are the equilibrium constants, and here's how you put them together. So here's our KEQ. It's always going to be the concentration of the products, and so concentration I'm going to represent with these brackets around my chemical symbol here. So my brackets around C means that it's the concentration of C, and then I'm going to raise it to the power of the coefficient that I find in the actual balanced chemical equation. And I'm going to do the same thing for all of my products. So here's my concentration of D, and I've raised it to the fourth power. So now I have the products raised to their powers of their coefficients, and now I'm going to do the same thing with my reactants. So now I have the concentration of A. Because there is no coefficient, that implies that it's a 1, so I'm raising it to the first power, which I don't have to explicitly state here. And then B squared raised to the second power here because of the 2 is my coefficient. So this is my generalized expression for my equilibrium constant. It's always products, concentration of products over reactants. And again, we're factoring in the balanced chemical process in our exponents here. And so based on this information, kind of using this and using the magnitude of this, I can figure out which side of my reaction is favored. Even if they're both going at the same speeds, I'm still going to have one side or the other, potentially, where there's more stuff, right? And that can just be for a lot of different reasons that go into the rates of chemical reactions and the chemistry itself and the energy of those particular reactants and products. So there's a lot that goes into it. But for our purposes, and the purposes today, I want to talk about how we can write these equilibrium constant expressions. That's what this whole thing is, an equilibrium constant expression. And then what the magnitude of that number is going to tell you about the equilibrium. So that's kind of going to be the focus today. So let's look at a real example instead of just my fakey one. Let's look at the Haber-Bosch process. So if nitrogen gas, and then 3 of my diatomic hydrogens go to form ammonia. Then we'd say, okay, well, if I want to write my equilibrium constant expression for this, then I'm going to say that my K is equal to the concentration of my products, which in this case is my ammonia, raised to its coefficient, which is a 2. So whatever the concentration is of ammonia squared. In general, the concentration that we're talking about is molarity. So it's in moles per liter in general. You can find concentrations in others, and there's a relationship between concentration and things like partial pressures and gases. So again, there's a lot of interchangeability with these types of things. But for our purposes, let's just call this concentration, and we're going to use molarity as kind of the standard. Then we're going to have this over the concentration of our reactants. So I'm going to have nitrogen raised to the first power because there's no coefficient, meaning it's just the one, times my hydrogen raised to the third power. Okay, so that's my equilibrium constant expression. Okay, so if I had a value for this, then that would tell me whether or not this reaction at equilibrium is going to favor the formation of the products or favor the formation of the reactants. And how does it do that? Well, if this number is big, right, if I have a large number, a large K value, you know, and on the order of really big, like, you know, millions, billions, kind of 10 to the 10th, 10 to the 12th kind of magnitude. So if we have a large KEQ value, then that means that the products are favored, right? It means that I must have a much larger numerator than my denominator. That's just mathematical, right? So my products must be favored there. Favored. And if I have a really small KEQ, and again, small for a chemist is really small, right? So we're talking about, you know, 1,000,000 times less than 1, 1,000,000,000 times, so we're talking micro and nano kind of scales, or 10 to the negative 12th or 10 to the negative 15th kind of values. So if we have really small values for that equilibrium constant, that must mean I have a really large denominator, which means I have a large concentration of my reactants. So that means that my reactants are favored. Now, if I have a KEQ value that's kind of in the 1 range, so if KEQ is around 1-ish, it's nice and scientific, right? It's about 1-ish even. Then, you know, in different texts define this in different ways. You know, if you're looking at kind of an introductory level, that gives you kind of a range. But I like to think about anything that's near the 1-ish range gives you a KEQ value that says that you have a pretty balanced relationship between the concentrations of your products and your reactants. So because it's a pretty balanced one, there's no real favoring of reactants or products. I would even hesitate to go balanced-ish concentrations between the two, right? Or at least just that there isn't one clearly favored over the other. All right, so let's look at another example and practice one more time. And then we'll talk about kind of some logistics here. So let's do this PCl5. This is one of my favorite compounds. I like it because it breaks the octet rule. A little bit of a rebel. Rebel without a cause. All right, so I have phosphorus pentachloride, and it is decomposing into our phosphorus trichloride and our chlorine gas. Okay, so if I was going to write an equilibrium constant expression here, then it's going to be equal to the concentration of my products, PCl3, raised to their coefficient, which in this case is 1, times my other one, chlorine, which again, coefficient is 1, over the concentration of my reactants, which is PCl5. Okay, now here's kind of the tricky bit, and this has to do with the type of equilibrium that we had. Now, in the first example that we had in the Haber-Bosch process, we had all gases. This is what is called a homogeneous equilibrium, meaning that all of the species are in the same phase. So if I have everything in the gas phase or everything in the aqueous phase, that would be a homogeneous equilibrium. If I have phases that are different, that's what is called a heterogeneous equilibrium. And a heterogeneous equilibrium is going to have a slightly different KEQ value, or at least it has the potential to, because I can talk about the concentration of a gas, right? Gas particles are so dispersed that I can talk about how many moles I have and how many liters. That's sort of the basis of things like Pivnert, and using those gas laws is that I can compress down those gases, I can expand them out. So I can talk about the concentration of gas particles in ways that I can't for liquids and solids. So if we look at this term right here, my potassium pentachloride here is a solid. So when I'm talking about the concentration of a solid, so if I just have a chunk of potassium chloride here and I said, well, what's the concentration? How concentrated is this solid? Then it breaks your brain, right? It's sort of like 100% of it is the solid, right? And that's basically true, right? So solid particles are really tightly packed together, and 99.9% of the actual sample itself is the solid particles. So you can't really talk about the concentration of a solid because it's essentially just 100% of that is. So if it's just a 1, then I don't include it in my expression. So I'm only going to include things in my equilibrium constant expressions that I can talk about the concentrations of. Otherwise, it just doesn't make sense. Or I'm just multiplying by 1, so it doesn't really matter anyway, right? So I can talk about the concentrations of gases. I can talk about the concentration of aqueous solutions, because that's how I measure them. But I'm not going to include pure solids or pure liquids. So for example, if you have water in your chemical reaction in some way, shape, or form, then that water is not going to be included, because if I had a beaker full of water here and I said, well, what is the concentration of my water? Then you would look at me and you would say, well, it's all 100% of it. What? You can't talk about the concentration of pure liquids. And I would say, you're correct. And then we're not going to include it in the equilibrium constant then. So this is kind of an introduction to the way that we think about this. The magnitude of these numbers then gives us information about this particular reaction. So what if I told you that this one is 2.1, so K is equal to 2.1 times 10 to the 7th? What would that mean? Well, that's a big number, right? Something on the order of magnitude of 10 to the 7th is a large number. So if it's a large number and my equilibrium constant expression is just equal to the concentration of my products, that must mean I have a lot of products, right? This number is equal to these concentrations. So there must be a lot of them. And if there's a lot of them, that means that the products are favored. So being able to interpret this value, being able to come up with this expression, and being able to relate it back to the balanced chemical equation is going to give you information that's going to be important for solving equilibrium type problems moving forward. And if you have any questions on this, as always, don't hesitate to reach out. Otherwise, I will talk to you again soon.